My name is Yu-Lun Hsieh, a senior student from National Taiwan University, and my advisor is Dr. Yanfu Guo. And today I want to share with you the research on a solution for automatically monitoring the dispersion and movement chicken flock using machine vision. So this is my outline. Let's start with the introduction. And Taiwan has a significant poultry industry. According to up-to-date statistical data, there were 50 million broilers raised in 2022. The production value is 56 billion new Taiwan dollar, which accounts for 28% of total production value in 21 different livestock. In Taiwan, Taiwan native chicken are one of the distinctive poultry industries in our country. They are loved by the consumer due to their flavor. Compared with broiler, Taiwan native chicken has a longer breeding cycle. Thus, monitoring chicken's behavior is extremely important. Taiwan native chicken are more active than broilers. A chicken's movement may be influenced by their health condition, temperature, humidity, or even the condition of bedding material. Also, when they feel uncomfortable, they tend to walk less or huddle together. Hence, the movement and the dispersion of chicken can serve as key indicators for the health condition of chickens. And to ensure quality, poultry requires intensive care. And traditionally, farmer patrols chicken house personally to check on the flocks. This method is not only laborious and time-consuming, but also heavily reliant on the farmer's experience. And furthermore, frequent patrols can easily introduce external diseases into poultry houses. Taiwan is facing several problems. According to the statistical annual report, the workforce in Taiwan's agriculture, forestry, fishery, and animal husbandry is continuously shrinking and confronting the issue of aging population. Due to these reasons, we need to find ways to overcome these challenges. So, our research aims to develop an automatic system that can use embedded systems to collect chicken house videos automatically and quantify chicken's dispersion and movement using machine vision. With the idea, the object is to quantify chicken's dispersion and movement. So, before we start, let me introduce the system pipeline. Our research involves collecting videos in chicken house through fisheye cameras and using 5G high-speed internet transmit them back to our lab server. Then we separate our system into two parts: the quantification of dispersion module and quantification of movement. In the dispersion module, UOV7 is used to detect chicken's location in videos. After that, the result needs to be calibrated due to fisheye camera's distortion. And finally, the nearest neighbor index can be estimated based on calibrated results and quantify and this value can represent the dispersion. Next, in movement module, videos also need to be corrected because of the fisheye camera distortion. Then we applied optical flow method to quantify movement. Lastly, a linear regression model is utilized to convert the optical flow value to the explainable value. So, for data acquisition, currently we separate chicken house into three parts, and we have installed one embedded system in one of it. The embedded system consists of a Raspberry Pi 4 single-board computer and two 220-degree fisheye cameras. As shown on the diagram, this system is installed on the beams of the chicken house. And we record high-quality video of chicken houses, enabling us to monitor the chickens without disturbing them. And here's the details. So let's get into the dispersion module. For the aspect of dispersion, we train a deep learning model to recognize the position of the chickens. Before training the model, it's necessary to label the collected chicken images. In our study, we use label image for annotation, and we have a total of 800 annotated images, which each image has at least 250 bounding boxes. The training and the testing data set are split into an 8:2 ratio, and here's the annotated images. Next, the images that have been annotated are used for training the Yu-Lun model. Yu-Lun is an object detection model which is known for its high accuracy and real-time performance. And our model is trained to predict and detecting the position of individual chickens. Here are my learning details. And during the training process, we employ data augmentation to enhance our model's robustness and accuracy. These techniques include horizontal flip, mix-up, mosaic, and Hsieh. Since fisheye cameras are used for recording videos, it's necessary to correct the distortion caused by the fisheye cameras. Left-hand side is the original videos, and the left-hand side, right-hand side is the corrected one. Once the data is calibrated, we can quantify the dispersion of chickens using the nearest neighbor index. The nearest neighbor index is a special statistical method which used to measure the degree of dispersion in a given area. And if the index is greater than 1, it indicates a sparse pattern. And if the index is less than 1, it suggests a dense trend. And our Yu-Lun model achieved a mean average precision of 89%. It demonstrates its effectiveness in detecting and predicting the positions of chickens. And here's the prediction video from the Yu-Lun model. As you can see, most chickens are predicted well. Then let's turn our attention to Graham of our model. Graham offers us windows to the thinking of our model. By visualizing where the model focuses within the images, we can understand which features are most influential in predicting chicken location. And as we zoom into the specific area of the Graham heat map, it shows that the model focuses on the boundary of chickens. When we aim to enhance our model's performance, we're confronted with challenges. We believe this may be due to two reasons. First is annotation inconsistency, and second is chicken overlapping. First, please look closer at the images. The red box is representing the ground truth, and here some blue box is for the model's predictions. And our model sometimes identify additional chickens not recognizing the ground truth. This causes a true-false case. So a solution to address this issue will be discussed later. And secondly, chickens may overlap by the water or feed pipeline and other chickens. This can cause difficulty of prediction. Next, movement module. And also, the video needs to be calibrated before we quantify the chicken's movement. To track and quantify the movement of chickens, we utilize the optical flow method, which calculates the motion patterns of objects in consecutive frames of a video and represent the motion of this object as vectors to obtain an optical flow field. By summing the vectors stored for each video, we obtain a numerical value representing the movement for that video. And optical flow can be implemented by different algorithms. In our research, we use Gardner-Farmbach algorithm. Now, chicken movement quantified by optical flow are measured in pixels per second. However, to make our findings more understandable, we're shifting towards a more explainable unit. Based on previous study using Yu-Lun and sorts, to track chicken movement, we adopt a linear regression model that allowed us to convert these pixel-based units into millimeters per second. So the model is based on analysis from 110 videos collected in a single day. The correlation coefficient is 0.87. This indicates a strong relationship which confirms the model's feasibility. So here's the results of the optical flow. It demonstrates the results of visualizing the velocity vectors in the videos. This movement value effectively differentiates between high and low active levels. So lastly, we compare the results of dispersion and the movement and attempt to find a correlation between them. We can find that they are both real high points in both charts. Therefore, we pick the video at that time. Looking into the video, we can see that the farmer walking and chickens were running and clustering in an area. As for findings, it's reasonable for the high value of dispersion and movement. A short recap of our research. In our research, our system shows promise in providing real-time performance monitoring and early detection of potential issues in poultry farms. In future, firstly, we will increase to 3 systems to get a comprehensive analysis from through the whole chicken coop. And secondly, we will consider more features such as ammonia, carbon dioxide temperature, and humidity to help us find a reason why chickens behave some abnormal. And finally, to boost our model's accuracy, we're introducing stricter annotation guidelines. This enhances data quality for better model learning. And thank you for listening.
Any question from the audience? Yes, don't you?
Have you considered using wide view angle based camera or wide view angle instead of using fisheye camera? Because when you use the fisheye camera, then the optical distortion is introduced to the image. Whereas if you use the specialized lens or camera, providing let's say about 180 degrees without that distortion, have you consider and then compare and then specifically chose fisheye camera over the conventional camera?
Okay, thank you for your question. And this is a good question. And I haven't tried using wide view angle cameras yet. So maybe we will proceed this in a future work.
Yeah, because definitely necessary. Because you put the unnecessary processing in the pipeline for the undistortion of the error. So it could be minimized when you use the different type of camera.
Thank you.
Yes.
I'm just curious, so what's the next step once you detect that dispersion and the movement? Then what's the purpose of that monitoring?
Okay, so we will analyze long-term values and try to find an abnormal pattern of the chicken flocks. So, and this can help farmers to find the early warning of the abnormal flocks, and this can help them enhance the poultry quality, the quality of chickens. And yes. Is this answer your question?
Kind of, but then what kind of action you have to do?
We will use like a RIMA to some English statistical method to find out if maybe like from May to September is this period chicken flocks is abnormal compared with the other times by the dispersion and movement.
Yeah, what I'm asking is, yes, you detected abnormality.
Yeah.
Then what's next? What are you gonna do with that? How are you gonna improve, or you estimate the yield, or what's the next after you detect the abnormality?
Do you need my help?
I'm just curious. I mean, that's the
Yeah, that's a good question. I'm
Yeah.
just wondering if he needs my help or not.
Yeah. So your question is, when I find some normal and abnormal movement and dispersion value, what will I do next?
Yeah.
So we will build an early warning system. Maybe it will monitor chickens movement and dispersion value, and if any abnormal value happens, it will talk us and give some warning information.
So that's the warning. That's the detection, right? So my question is, once you detect it and you got a warning, then what's the action from that warning?
Well, there are like several things that we can do. The first is to warn the farmers. So other than the warning time, the farmer doesn't have to enter the chicken house.
Okay.
So that's main purpose.
So management.
Yeah, we changed the management procedure. And second is that if we run the monitoring for several batches, we can find a like safety zone, say, okay, like within this zone, the chickens are doing fine. We really don't have to worry about those. And what Yu-Lun just mentioned about Arima is that because this is native chicken, their growth period is long. It's not only 4 or 5 weeks, and their dispersion and movement changes a lot. So we need some more sophisticated model to do the like statistic analysis. So I think he might went too far away. Yeah. So yeah.
Thank you.
You're welcome. Any other question? Songjo? Yeah.
I'm just wondering whether you are also planning or doing some research for more targeted, individualized precision.
You mean individualized chickens or?
Yeah, because my understanding is that people are trying to do the precision phenotyping so that they want to detect and isolate the bad chicken sometimes or the unhealthy chicken instead of just monitoring as flocks.
Yeah, I mean, that's a very good question. When you talk about phenotyping, that means like breeding. If we want to, okay, these parents, they'll give you a good son or daughter or some things like that. And we have to do individual tracking, like how much food they take and their growth in response or things like that.
Yes,
we are considering to do that in the following years. But for that one, we need RFID or some other technology instead of image. Because image, like for long-term tracking, like if you track the chickens for 5 minutes or 10 minutes or 1 hour, it's okay. But for like several weeks, probably image is not good enough.
Right.
All right. So let's thank Ms. Hsieh and thank you very much for joining us this afternoon.